We now want to look on the molecular level and understand how reactions occur on the basis of collision theory. Arrhenius proposed that molecules react upon completing a successful collision. If you have more collisions, you get more product. Before molecules react, they must attain what is called the energy of activation. Here we see A molecule reacting with B. It goes through a transition state, AB double cross, to yield product C plus D. For an exothermic reaction, this is what the potential energy looks like. For an endothermic reaction, we have the following. The activation energy, E sub A, is the minimum amount of energy required to initiate a chemical reaction. There is a temperature dependence of the rate constant. If we plot the rate constant versus temperature, we see the following parabola. K equals A times the exponent minus EA over RT. It's known as the Arrhenius equation. E sub A is the activation energy in joules per mole, R is the gas constant, T is the absolute temperature, and A is called the frequency factor. The alternate format is the logarithmic equation. Log of K equals minus E sub A over R times 1 over T plus the log of A. If you plot the log of the specific rate constant, log of K, versus the reciprocal of the temperature, you get a straight line. An alternate form of the Arrhenius equation can be given for two temperatures, T1 and T2. The log of K1 over K2 equals EA over R times 1 over T2 minus 1 over T1. It's important to understand molecular orientation. For example, carbon monoxide reacting with nitrogen dioxide yields carbon dioxide plus nitric oxide. Here are the two molecules. If there's an effective collision, we get product. But if there's not, we do not get product. A catalyst is a substance that increases the rate of a chemical reaction without itself being consumed. Again, the Arrhenius equation. If the activation energy is lowered, the rate constant increases. Here is a catalyzed reaction versus an uncatalyzed reaction. Notice that the potential energy for a catalyzed reaction is much smaller. That is, EA prime is smaller than E sub A. The rate of a catalyzed reaction is always greater than the rate of the uncatalyzed reaction, and that is because the energy of activation of a catalyzed reaction is less than the energy of activation of an uncatalyzed reaction. There are heterogeneous catalysts. There, the reactants and the catalysts are in different phases. Examples of this are the Haber synthesis of ammonia, the Ostwald process for the production of nitric acid, and also catalytic converters. In a homogeneous catalyst, the reaction and the catalyst are dispersed in a single phase, usually a liquid, and these are usually acid or base catalysts. Here's the Haber process. Nitrogen reacts with hydrogen to form ammonia. The catalyst is a mixture of iron, aluminum oxide, and potassium oxide. The Ostwald process is for the manufacture of nitric acid. Here a platinum catalyst is used. Very important to our atmosphere are the catalytic converters in our automobiles. Here carbon monoxide and unburned hydrocarbons react with oxygen in the catalytic converter to be converted into CO2 and water vapor. Also, the nitric oxide and nitric dioxide is catalytically converted into nitrogen and oxygen. There you see a cross-section of a catalytic converter. Enzyme catalysts involve an enzyme and a substrate, forming an enzyme-substrate complex. It's in the complex that the products are formed. Here we see the binding of glucose to hexokinase. On a molecular level, we understand that there is an enzyme and the substrate. Enzyme kinetics follows Michaelis-Menten kinetics. Here are the equations that show the reaction between the enzyme and the substrate to form the enzyme-substrate complex, and then recovery of the enzyme with the product.